All right, here we have a problem where the velocity as a function of time is given, a times the natural log of t plus 1 minus bt, where a is 10 meters per second and b is 1.5 meters per second squared. And the problem asks us to find delta x, that is the displacement, that is how far forward the car moved, or the object moved, for the time period of t equals 0 to t equals 20 seconds. And to find the acceleration at t equals 2 seconds. So the first thing I'm going to want to do when trying to solve a problem like this is to graph the equation. And the reason I want to graph the equation is I just want to have some visual idea of what's going on. So I plug this equation into my graphing calculator, and I find that the velocity looks like a function that starts at 0, goes up to just above 10, and then drops down to right around 0 at 20 seconds. So what this means is that the object starts at rest, it speeds up, it speeds up, it speeds up, and it continues to speed up until it reaches a maximum speed of just over 10 meters per second, and then it slows down and slows down and slows down and slows down and comes to rest just after the 20-second mark. And we are asked to find the displacement of the object during that 20 seconds. Well, since it has a positive velocity the whole time, I'm expecting it to have a positive displacement. It should be moving forward the whole time. So delta x should be a positive number. It should be moving forward. Also, it asked me to find the acceleration at t equals 2 seconds, which, if that's 5 seconds, 2 seconds is about right here. And it looks to me like it's still speeding up at that point. So I am expecting a positive acceleration. All right, we don't have to draw the graphs, but I find it useful in sort of understanding what I'm looking for. All right, so we are going to start with, to find delta x, we're going to start with the definition of velocity. And part of the definition of velocity tells us that displacement, that is the change in position, is going to equal the integral from time 1 to time 2 of velocity with respect to time. And this is, I'll put a little 1 next to that, and I'm going to come over here, and in my explanation, I'm going to say this is the definition of velocity. Okay? Now, to actually get my answer, I need to integrate. And so one of the math principles that we're working on this week is integration of functions. And so I'm going to put up here that we are using the math principle integration of functions to solve this problem. Okay, so now I need to actually do the work. So to find delta x for this problem, we are going to be doing an integral. And if you've never done integrals before, please watch my videos on integration. Also, look at the information sheet for this unit. Some integrals of basic functions are provided. So what we're going to do is find the integral from t1, that is 0 seconds, to t2, that is 20 seconds, of the velocity function, that is a natural log of t plus 1 minus b of t dt. All right, so now we have to perform this integration, and to do that, we are going to look up the integral of natural log, and the integral of natural log of t is t natural log minus t. But we're not taking the integral of t, we're taking the integral of natural log of t plus 1. So we do a couple of things. First of all, we pull out the constant. So this is going to be equal to a times, and now we integrate natural log. And again, the integral of natural log, let's say natural log of x, is x ln x minus x. But we're not doing x, we're doing t plus 1, so this is going to be t plus 1 times the natural log of t plus 1 minus t plus 1. Okay, so that was the integral of the first piece, and now we need to take the integral of the second piece, negative bt, so that's going to give me minus b times the integral of t, and the integral of t is 1/2 of t squared. And again, I've got a table of basic integrals and derivatives in the information sheet for this week. Okay, so we have performed the integration, and now what we're going to say is that we want to evaluate this integral from t equals 0 to t equals 20 seconds. And the way we do that is we first plug in t equals 20 everywhere we see t, get a value, and then we subtract t equals 0. All right, so let's go ahead and plug that in. So we're going to have a, which is 10, times, let's see, let me get this straight. I think I missed a parentheses here, because that a is multiplied by that whole thing. Okay, so it's 10 times t plus 1 is 21, times the natural log of 21 minus 21 minus b, which is 1.5, times 1/2 of 20 squared. So that's 20 squared is 400, so 1/2 of 20 squared is 200. Okay? So all of that minus 10 times. And now I'm going to be plugging in t equals 0. So 10 times 1 times the natural log of 1 minus 1. Okay, minus b, which is 1.5, times 1/2 times 0 squared, which is 0. Okay, so let's plug in the first one, 10 times 21, okay, 10 times the quantity, 21 times the natural log of 21 minus 21, close parentheses, minus 1.5 times 200. So that is 129.35 minus, and plugging in this second one, I get 10 times the quantity, 1 times the natural log of 1 minus 1, and then minus 0, so that doesn't matter. And I get negative 10 for that. So my total answer is 139.35 meters. Why meters? Because we're finding delta x. We're finding a distance, so it must be meters. Okay, and so now our answer should have two significant digits because the problem has two significant digits. So this is going to be 140 meters, and I make sure to put a box around my final answer because you want the person grading it to be able to find it. So all of that was part A, and I ran out of room. So I'm going to do part B on the back of the paper. So I flip over to the back of the paper, and for part B, we want to find the acceleration at a particular moment in time. So the definition of acceleration says that the acceleration is equal to the derivative of the velocity function. And this is the definition of acceleration. And in order to solve this, I need to take the derivative of a function, and that is one of our principles that we're looking at this week. So I'm going to put that in my explain part. So let's look at this template that we have for all of our problems. We have to execute the problem. That is the part that you are likely familiar with from every math and science problem you've done your whole life. You have to do the problem. And there are reminders here. It says draw a diagram if helpful or required. We did that. Start from first principles. And what that means is we have a list of principles that we are going to be using. And that list of principles is either going to be provided to you in the notes for that week, or you'll get them from watching the videos. But we need to always start at the beginning of the problem. We can't start with a memorized equation that gives us the answer right away. We usually have to do some deriving. So we're going to start from a first principle, we're going to show each steps, and we're going to get the correct answer with the correct units and the correct significant digits. And that's the part of solving a problem you're probably used to. What you may not be used to is that I also expect you to explain and evaluate your problems. So in the explain part, we have 3 steps. First of all is what physics or math principle are we using to solve the problem? And sometimes there's only one, sometimes there's several. This time, this problem is about integrating functions and taking the derivatives of functions. So those are our principles for this problem. The next thing we have to do is anytime we use a special case equation or an empirical law equation, we have to justify why that's appropriate for this situation. Now, we don't have that this week, but what we do have is some definitions, and so I went ahead and put those in here, even though it's not strictly required. Anytime you use a special case equation or an empirical law, you are required to justify its use. Definitions are always true, so we don't really need to justify whether or not we're allowed to use them, but I still labeled it anyway. And then part C of the explain part is what numbers did you plug in that were not explicitly given in the problem? Now, this will come up in future quizzes. I don't really think it's going to come up in today's quiz, so this is not applicable for this problem. All of the numbers that we're plugging in come directly from the problem. There's never a time where we're plugging in a 0 where it wasn't given to us. There's never a time we're plugging in some number that wasn't given in the problem. So we don't have to worry about that for this problem. All right, well, let's finish here. We are now looking at finding the acceleration at 2 seconds. So the first thing I need to do is take the derivative of the velocity function. So the acceleration as a function of time is going to equal the derivative of my velocity function, and my velocity function is a times the natural log of t plus 1 minus bt. All right, so my acceleration, again, now we're going to have to look up some derivative rules in the tables that I provided, and the derivative of the natural log is 1 over x. And here, my x is t plus 1, so the derivative is 1 over t plus 1. So this gives us a divided by t plus 1 for the derivative of that first part. And for the second part, the derivative of t is just 1. So we end up with b times 1, which is just b. Okay, and now that is 10 divided by t plus 1 minus 1.5. And this 10 is meters per second, and this 1.5 is meters per second squared. And so we are going to end up with 10 meters per second divided by t equals 2. 2 plus 1 is 3, divided by 3 seconds, minus 1.5 meters per second squared. Plugging that into my calculator, I get 1.8333 meters per second squared. Two significant digits, 1.8 meters per second squared is my acceleration at 2 seconds. All right, and that means it's still speeding up. And when I look at my graph, I can tell it is, in fact, still speeding up at 2 seconds. So my answer seems reasonable. The last part of every problem is to evaluate. It says, put your answer into context by comparing it to an appropriate reference value. If the problem has multiple parts, pick only one part to evaluate. If no reference value is possible, what is the significance of the answer? Well, that last part doesn't apply here. We've got two answers, 140 meters or 1.8 meters per second squared. And we need to pick one of those to compare to a suitable reference value. And I'm going to pick the acceleration. So I'm going to say the acceleration at 2 seconds of 1.8 meters per second squared is less than the free fall acceleration on Earth. Now, why did I pick that? Because the free fall acceleration on Earth is known as g, and that is a number that we will all have memorized very soon. The free fall acceleration on Earth is 9.8 meters per second squared. Okay, so this is an evaluation of an answer. And what we're doing is we're picking one of our answers, and in this case, the answer we picked was the acceleration of the object at 2.1 second, at 2 seconds. So the answer is the acceleration at 2 seconds. I also wrote down the actual answer, 1.8 meters per second. Next, I compared it to something. The comparison is something like is less than, is more than, is about equal to, is much less than, is much more than, things like that. So I compared it to something, and again, two things. I named the thing I compared it to, the free fall acceleration on Earth, and I also gave the value of the free fall acceleration on Earth. So I'm really looking for 5 things in the evaluate section. What is the answer you're evaluating? What is the number of the answer you're evaluating? What is the thing you're comparing it to in words? What is the number you're comparing it to? And the actual comparison. Is it greater than, less than, or about the same? So these will be required for every problem this semester. All right, so hopefully this video serves two purposes. One is to give you an example of how to solve some of the problems this week, and the other one is to show you how we're going to be solving all of our problems using the execute, explain, and evaluate method.